To predict the future state of a moving object, we must first isolate it from the physical chaos of the real world. Mechanics maintains a divide between the causes of motion and the mathematical description of that motion. This title slide introduces our specific academic focus, kinematics. Kinematics is the mathematical description of an object's displacement, velocity, and acceleration. Displacement is the change in position of an object, represented as a vector. This chart illustrates how kinematics differs from dynamics. The right side shows dynamics, which accounts for mass and force, the physical causes behind movement. We will focus on the left column, where only the dimensions of length and time are involved. By setting aside mass and force, we create a geometric playground where motion is decoded using two variables, space and time. To build this framework, we reduce the object to a mathematical particle, a dimensionless point in space. This slide defines velocity as the rate of change of displacement over time. In calculus, this is the first derivative, expressed as v equals dx over dt. Because velocity is a vector quantity, its positive or negative sign indicates the physical direction of travel. This algebraic equation has a geometric counterpart. This graph shows that the derivative, dx over dt, is the gradient of the displacement time curve. This relationship is reversible. If velocity is the derivative of displacement, then displacement is the integral of velocity. In the velocity time graph on the right, displacement is the accumulated area under the curve between two specific points in time. Calculus and geometry function as two distinct ways to describe the same physical reality. Now we move one layer deeper to analyze the concept of acceleration, the specific rate at which velocity itself changes over time. Acceleration is defined formally as the first derivative of velocity with respect to time. The geometric rules we established for velocity apply here as well. As shown in this graph, the derivative matches the slope of the velocity time curve. When acceleration is constant, the calculus resolves into a simpler algebraic form. We use Formula 4 when the rate of change does not waver. Establishing these first and second derivatives provides the necessary framework to dissect a moving object's timeline. We can apply these principles to a particle tracked by a continuous mathematical function. In this example, the displacement of the particle follows an exponential decay function. By applying the product rule, a calculus technique used to find the derivative of a product of two functions, we derive the velocity formula. Differentiating a second time yields the underlying acceleration formula. This data allows us to find the exact moment the particle is furthest from its origin. Maximum distance occurs when velocity reaches zero. In this specific case, that happens at exactly 1 second. The visual proof confirms this. The peak of the displacement curve aligns with that 1 second mark. Maximum speed, however, does not always occur when acceleration is zero. The velocity time graph shows that the highest magnitude actually occurs at the very start of the timeline, before the derivative ever hits zero. While calculus provides theoretical precision, plotting the geometry is necessary to account for behavior at the boundaries of time. This logic also applies when we have no underlying equations, only raw graphical telemetry. This is the velocity time readout of a particle starting from rest. We want to determine the maximum magnitude of acceleration using only these visual lines. Magnitude represents the absolute size of the value, ignoring its direction. Acceleration remains the visual gradient of the velocity curve. We can find the answer by comparing the steepness of these three line segments. The third segment has the steepest gradient on the graph, despite its downward direction. Stripping away the negative sign gives us a maximum acceleration magnitude of 2 meters per second squared. Geometric analysis can extract precise rates even when the underlying calculus is unknown. Finally, we must distinguish between total ground covered and net change in position. Displacement is a vector quantity, meaning movement in opposite directions will mathematically cancel out. To find displacement, we calculate the area bounded by the velocity time curve. As this summary shows, calculating final displacement involves subtracting any area falling below the zero axis. Total distance is a scalar quantity, representing pure accumulation regardless of direction. Finding distance involves summing the absolute values of all areas, treating every region as a positive addition. The presence of a negative sign changes the physical interpretation of the data, distinguishing between a particle's net displacement and its total travel distance. Ultimately, kinematics provides a rigorous mathematical map of physical motion by applying the fundamental rules of vectors, limits, and space.